Hello, STEM students. Welcome to your second STEM challenge. Today's challenge involves engineering, physics, and math, and it's called Paper Bridge Challenge. Look around you. Bridges are everywhere. They come in different shapes, designs, and materials of construction. But before we get into the challenge, we need to talk a little bit about some physics, namely some of the physical forces involved in bridges. The first force is compression. For instance, this brick I try to squeeze it. I am trying to compress it. And as you see, a brick, a very rigid thing, resists that squeezing or compressing force. Second force involved in bridges is tension. And that is a force that tries to pull things apart, tries to stretch them and make them longer. This piece of cord that I have, if I pull it apart, it resists that tension and doesn't get any longer. It resists tension. Other forces are, for instance, torsion, which is a twisting force, or shear, which is a sliding force. We won't talk about those very much, though. An example, as I said, of something that resists compression is stone, or bricks, or concrete. It's very resistive for compression, but is not flexible. Also, it doesn't resist tension very well, because if you had a lot of force, you could pull those bricks apart. And also, it is not flexible. If you flexed a stone wall, it would crumble. For tension, though, pulling apart force, steel cables are very good at resisting tension. They're flexible, but they're not compressible. For instance, if I had a cable and I try to compress it, it just goes slack. Let's look at some different types of bridges. The first is a suspension bridge, and the classic example of that is the Golden Gate Bridge in San Francisco, California. What's characteristic about suspension bridges are long cables that go from a tower to a tower, and the roadway is suspended by cables coming down from that main cable. These bridges are designed for very long spans, possibly. The main span in the Golden Gate Bridge from here to here is 4,200 feet. That's over 3/4 of a mile, all suspended over San Francisco Bay. Some other examples are the London Bridge in London, England, has some components to it that are suspension related. And here's a bridge that maybe you've kind of seen. It's a walking suspension bridge. And if you've ever been on one of these, you know that they are very wobbly and they sway, but that's okay because steel cables are taking up your weight by tension, and they're very flexible so that bridge can move. As I said, the cables in the Golden Gate Bridge and any suspension bridge are under tension. That is, they're trying to be pulled apart. The second kind of bridge that we'll talk about are arch bridges. So named because of their obvious shape, they are arches. Here's one that's in two of them that are in Indianapolis. The Meridian Street Bridge over Fall Creek is an arch bridge, and you can see there's the arch. The old Washington Street Bridge in downtown Indianapolis is also an arch. This one is made out of concrete. And you'll see arch bridges are typically made out of very rigid materials like stone or concrete. That's because stone and concrete are very good at resisting compression, which is the squeezing force which these bridges exhibit near their tops, because the stones, the weight of on the top of the arch is squeezing those stones together, and they don't budge because they are very incompressible materials. Other types of bridges, there's a simple one called beams, which are simple beams strung over some pylons to hold them up in the middle. They're simple, flat designs, relatively short spans, and here's a couple that are in Indianapolis. The CSX Railroad Bridge, which is Interstate 65 and 70 near downtown Indianapolis. Here's another one that is at the Indianapolis Museum of Art. And here's one down in Florida, in the Florida Keys. It's Route 1A. And you'll see that one of the spans of this bridge in the Florida Keys is made out of steel reinforced concrete. The other is made out of just steel. And the last kind of bridge I want to talk about is a truss bridge. A truss is a framework, such as this, that can be either on the top of the bridge or underneath the bridge. Doesn't matter. They both very nicely support the bridge. Here's one that's you might have seen in Indianapolis. It's the Monon Trail over Fall Creek. What truss bridges are simple frame designs. They span medium lengths. And what you'll see in truss bridges is a characteristic triangular shape. Turns out that triangles are structurally very sound shapes in engineering and used for supporting heavy weights. You'll have a chance to use some of these triangles perhaps in the bridge challenge that's coming up. Just to review some of the forces: compression, the squeezing force, tension, the pulling apart force. I created this little model of a bridge, just a simple flimsy piece of wood spanning between two bar stools, and I put these clamps on it just to show you how the top of the bridge support is in this resting state is tight and the bottom is very slack. If I put a weight on it, such as this jug of water, it has a downward force that kind of bends the flimsy board, and what you'll see is the bottom string went from loose to very tight. That's tension, pulling that apart. And if I didn't have that line in there, this would have crashed down and would have hit the floor. Also note that the top string, which was tight in the resting state, became very slack in the weighted state, and that is compression. It's squeezing it together. So if I took and built a truss bridge on top of this, similarly with the compression and tension, if I put weight on it, there's compression on the top and tension on the bottom. I'm going to show you an example now of compression and tension in a real life situation, and that is this bridge that collapsed. You'll see it is a truss bridge. You see the characteristic triangular shapes. A heavy weight was put on the middle of it, maybe too many cars, maybe a heavy truck, and the top of it got compressed. It got shorter, and the bridge collapsed as a result. All right, let's get to the paper bridge challenge. You're going to need some supplies for this. You're going to need sheets of paper. Preferred would be some 8.5 by 11 copier or printer paper, but anything else will do. You could use printer paper, newspaper, junk mail, but do not use cardboard. That's not for this experiment. You'll need some end supports for your bridge, at least 2 inches tall, and you can use wood blocks, stacks of books, boxes, anything you can find. A glue stick or glue would be optional for one of the categories of this challenge. A ruler and scissors would also be optional. You might be able to use those. And you'll need a bunch of US coins for weights to put on our bridge. All right, here's the challenge. Design, build, and test a bridge that is strongest based on the weight supported per number of sheets of paper that you use to build it. The winning bridge is the one with the highest calculated ratio, math, ratio of weight supported per number of 8.5 by 11 sheets of paper that are used to make it. So what you'll want to do is put up a little bridge, apply weights gradually until it collapses. The weight supported that you use in this calculation is the weight of the bridge, the weight that you put on the bridge before it collapsed with that last weight that you added. There's two categories to this challenge. One is to use paper only. The other is to use paper and glue. Here's the rules. The bridge can be made of paper only, that's category A, or paper plus glue, that's category B. The bridge can be supported at the ends only and must span at least 8.5 inches. I'll show you a diagram of this in a little bit. The weights must be placed on the bridge within 1 inch of the center of its span, that is from one support to the other. Also, the bridges cannot be attached to the end supports. They just have to be resting on them. Here's the weights that you can use. These are US coins, and here's the weights. A penny weighs 2.5 grams, a nickel weighs 5 grams, and so forth. What you do is you add these coins gradually to the middle of your bridge until it collapses. All right, here's how you do some of the calculations, the math part of it. Example 1, we used 2 pieces of 8.5 by 11 paper to construct the bridge. Before it collapsed, it supported 4 quarters and 6 pennies. So the calculation goes like this. The weight that was on the bridge when it collapsed was 4 times 5.7 grams, which is the weight of a quarter, plus 6 times 2.5 grams, which is the weight of a penny. So 4 times 5.7 is 22.8, and 6 times 2.5 is 15. You add those together, you get 37.8 grams. So the ratio that is used to calculate how good the bridge was is the weight supported divided by the number of sheets. In this case, it's the total weight, 37.8 grams, divided by 2 sheets, or 18.9 grams per sheet is the ratio. In the second example, we used 1 piece of paper, and before it collapsed, it supported only 9 pennies. Oops, I got that wrong. It's 8 pennies. 8 times 2.5 is 20 grams supported. The ratio is the weight divided by the number of sheets, which is 20 divided by 1, or 20 grams per sheet. So which bridge construction won? It's the one in example 2, because the ratio, 20 in the case of the second example, is greater than the ratio in the first example, 18.9. All right, here's some examples of how you set it up and some bridges that you might try. Again, the supports are 8.5 inches apart and at least 2 inches tall, and you just put a sheet of paper over it and you start laying your weights or your coins in the middle of it until it collapses. This piece of paper has been curved slightly because if it didn't, it would just bow down in the middle and wouldn't support anything. Here's another example. Try this design. It's where I folded the edges of the paper upward. That looks a lot like a beam design. And it can support some weight, but hey, Willett, get off my bridge. You're going to collapse it. Here's some other paper bridge ideas for you. In the paper-only category, you can fold paper in many ways. Look at these triangles. They help add strength to your bridge. So in the paper-only category, these are some ideas. In the paper plus glue category, you can make cylinders or triangles or square sort of beams, or triangles in another way here, or you can even construct an arch from a piece of paper. So that's it. Happy bridge building and good luck, and can't wait to see what your results are.